See, I'm connecting. Okay, so you can see my screen and you can see me.
Yes.
Hi,
okay.
Everyone. Yeah, should I wait?
Yeah, give me one. Oh, okay, let's get started. So our last speaker is Professor Marine Boutin from Purdue University. She is an associate professor in the School of Electronic and Computer Engineering, and also with a courtesy appointment in the Department of Mathematics. Her research is in the area of signal processing, machine learning, and also general applied mathematics. She has received many awards, including Purdue's Seed for Success Award, the Eta Kappa Nu Outstanding Faculty Award, and the Outstanding Teaching Award. She's currently associate editor for 2 EEE journals. One is Signal Processing Letters, the other one is IEEE Transactional Image Processing. So I'm very looking forward to her talk, which is a highly likely clusterable data with no cluster. So Marie, it's your time.
Thank you, Jianshao. It's a pleasure to be here presenting. We have a beautiful day here in West Lafayette. I don't know if you can see, we have first snow of the season in the background, and you're seeing the engineering fountain covered with snow. So on that, let's talk technical now. So this talk is about research that I did to try to understand the structure of high dimensional data and understanding this structure so that we can exploit it in machine learning application. It's not research I did do alone. This particular talk is in collaboration with my students. So there's Alden here. You can see participated a lot. Also Tarun, who is now at Qualcomm, and Sangchun, who is now at Google. So, all right, So the big question I want to answer is, what kind of structure does empirical real high dimensional data have? So what I mean by empirical data is you run an experiment, you have some sensors, you collect some data, or you take pictures, real data, and then high dimensional data. What kind of structure does it have? Why do we ask this question? Well, of course, in machine learning, we're going to exploit structure to build models. The easiest example might be you have 2 classes that you want to classify, and you get some samples from class 1, and they lie here in your space. And then you get some samples from class 2, and they lie a little bit over here and a little bit over there. So, collecting together and forming little clumps in different regions of the plane. And then you can use that to say, well, I'm going to divide my space into regions where over here I'm going to say it's class 2, and over here it's class 1. Right? So you learn from the structure of the data, and you build a classifier. So this is, of course, a very low dimensional illustration of what's going on. And we have to be careful, because our intuition in low dimension really does not carry over to high dimension. And one thing we need to be cognizant of is that when we're working with data points, we want to make sure that what we're finding is statistically significant, because what we have is samples, random samples. We learn from these samples, but we want to make sure that what we find is going to hold in the future when we draw more samples. So, if I only have 2 points from one class and 1 point from the other class, and I decide, oh, I'm going to draw a separation right here because that's what it looks like. Well, maybe in the future, I'm going to end up having points from the first class being here. And I didn't know this because I didn't have enough points or to figure this out. So we must make sure that the structure we find are truly there in the underlying probability density functions that the points are sampled from. So that's something to keep in mind, is especially important in high dimensions. All right. So what do we know about high dimensional data? Is there something that we know already? Well, we already know that, because of the sparsity of points in high dimensions provides a lot of space. And even if you have millions of points in a high dimensional space, say dimension 50, your points are going to be very sparse. And what happens is that you're not going to find clusters per se in a high dimensional space. Why is that? Well, it's very simple. proof, and I always show my students when I teach, because we need to realize this is really a mathematical property of spaces, is if you take a unit cube in a d-dimensional space, so say you're in RD and D is going to be large. So what is the volume of that unit cube? So each side has length 1, right? So the volume of the cube is 1 to the D, so it's 1. But if I remove a little shell around my cube of thickness epsilon, so I'll take a little epsilon here and I remove it, a little epsilon here and I remove it. I just carve out a little shell all around my cube of size epsilon everywhere, so that the side length now becomes 1 minus 2 epsilon. So this is 1 minus 2 epsilon, 1 minus 2 epsilon. So if you look at the inside of that cube, it's going to have volume 1 minus 2 epsilon to the dimension D, and this will converge to 0 as D goes to infinity. So in other words, the inside of your cube is going to have 0 volume. All the volume will be concentrated inside that shell around the cube. And so unless you have a degenerate probability distribution, when you draw samples from your distribution, you'll have a 0 probability of having samples inside the cube. And therefore you cannot have a cluster inside any region, any cube, because of that 0 probability there. So we don't actually expect to encounter clusters in high dimension. And this is something that's very well known, but in fact, people realized that back in the 1980s when they were building database indices to search them quickly. And they realized that, starting from about dimension 23, the index structures that they were building were not actually saving them any time. And so that's because you really don't have clusters in high dimension. You don't expect to have them. And so, so what we know about high dimensional data is that there's no cluster. You don't expect cluster in the high dimensional space. You don't expect points to clump together in the high dimensional space. And so what we do, of course, in real life, in applications, is we try and find those clusters and projections of the data onto lower dimensional structures within that space. So that's very well known. But we have to be a little bit careful, because so I think let me use the Bourbaki symbol here. You know that symbol? It's a curve coming up, so we have to be a little bit careful. We have to be careful because when we project, obviously we can destroy structure. So structure can be destroyed by projection. I think we're all aware of that, and we're all careful about, the fact that the projection doesn't contain all the information that was in initial data. But the other thing that we must also realize is when we project, we might create structures. And that's something that I think we forget sometimes. A structure can be created by projection. And so, what happens is that when you choose a projection, you can end up finding a structure that is really depending on your choice of projection. And so the structure you find depends on either the mathematical framework or the algorithm that you use, and is highly dependent on the projection that you've chosen. Is that the one correct answer? If somebody else was to find another structure, would they be right? Who has the right answer? Who has the right structure? Or more importantly, is there just one structure to be found? Or are there several, depending on how you observe it? So I think we need to think of clustering as a fundamentally potentially ill-posed problem, not just because we don't know what metric to use to find our clusters, but even if I choose a criteria for clustering, there may be different results depending on how I project my data to different spaces. And this talk is going to highlight that a little bit. So we know these things about high dimensional data. We know that there's no cluster in high dimension. We know we have to look to lower dimension spaces to find those clusters. And what we're going to find in this talk is that actually we know a little bit more. That first of all, what we will uncover is that clusters are actually in empirical data, clusters are actually fairly likely to appear if you just do a projection on a random line. So, oftentimes we're trying to project on higher dimensional spaces, 5, 10, 15, but actually if you just project to a space of dimension 1, and if you pick that space at random, turns out it's actually very likely that you'll find some non-trivial structure there and some clustering structure. And the other thing we'll find on the talk is that each of these structure, each of these clustering is going to lead to groupings in the original data. And these groupings might not actually be consistent with one another. Yet, the groupings are, the clusterings and the groupings are statistically significant. So they really exist in the data. And so I hope this will all make sense once I cover the details. Notes here. All right, so let's explore a little bit this concept of projecting data on a random line. And I like to start with, show some results of experiments. And this is one that I like to present because it's something you can do at home. It's something that does not require any, very special high dimensional data. It just requires, taking pictures. A picture is a nice source of high dimensional data that we all have at home. And so if you want to try and make sure that what I'm saying is correct, just go and try it. So what happens if you take a picture and then you look at all windows of a certain size in your picture? In this particular case, I took 7 by 7 windows. This is a color picture. So each pixel has 3 values, the R, and G, and the B. And so if I take a 7 by 7 window, I end up with a vector of dimension 147. So window, I see that as a point in R to the 3 times 49, 7 by 7. In other words, R to the 147. So I have my picture and I take all the windows. So I end up with a bunch of points. I view my picture as generating data in high dimension. And let me draw the picture here. So these are my points in high dimension. So what I'm going to do is I'm going to draw a random line through the origin. Choose it at random using a random number generator, like a IID Gaussian coordinates independently. So let's say here, right? And I'm going to take all these windows. I'm going to project them onto this line. So you end up at the end with a one-dimensional. A set of one-dimensional data points. And what I have on the right-hand side of my screen here are the first 2 projections that I got. So I did a histogram of the points so we could actually see their distribution in each case. And so this is the first projection that I got. That's a histogram. And as you can see, there's, one clump and that's it. And that's about what you expect. Right? No, there's no real structure there. And I mean, this might be a little bumpier, but that's not really that obvious. So, something pretty generic, not very useful, does not contain much information. But the second one, and this is a tree experiment, these were 2 random ones that I drew. The second one that I obtained has something very interesting, namely the histogram of the projection of those windows is bimodal. You can see there's a bump here and there's a little dip here, right? And that is very surprising. This is not at all something you expect to obtain, but that's something that's very interesting because we can see there's a structure. You can see, okay, there are 2 types of windows in this image, and they're the ones who are right of the dip and the ones who are left of the dip. This is the big group here and then the small group there. They're clearly distinguished, and you could find out, what's different about them, and it's a natural category that arises just from this random projection. And again, this is just one drawn at random. I did not draw 100 and pick one that looked nice. These are 2 that I drew, and that actually I have a total of 4. These are the first 2. I can show you the third, and the fourth. They look approximately like the first and the second. And so this was done at random. So we did a bunch of experiments like this. In fact, we discovered this phenomenon when studying images of fingerprints. And this was research with my student Hector Santos Villalobos back in the days, where we realized that, look, if you want to cluster fingerprints, you can just do a random projection and then you will see a clear binary clustering. We started playing with a lot of image data sets and wrote a paper on this where we found that, image data sets, if you project them on random one-dimensional subspaces, they tend to cluster with a very high likelihood. Not every single projection looks like this. There's still some that look like one clump, but by and large, you get a lot of these very surprising projection that show a clear division of the pixel into 2 classes, binary clustering. And so, yeah, so this was a very surprising but happy discovery. We realized, clustering images is actually not that difficult. And then we started exploring other types of high dimensional data sets that were, that contain real empirical data. And we found that phenomenon to be quite actually common. You would do a random projection and find a clustering. And so, well, of course, this suggests building a clustering algorithm, right? Let's just build a clustering algorithm and see if it works really well. And so very simple clustering. You do a projection, a random projection, and then you threshold the data into two groups. So we call that a TARP, for thresholding after random projection. And if you want to make sure you get a good one, maybe you repeat this n times, like maybe through 30, 40, 50 times, and you pick the best clustering that you get. So that's a super simple clustering method. It essentially works in 1D. You find the clustering in 1D. And so it's very quick. And more importantly, once you have the 1D projection, it's easy to make statistical tests to make sure that what you're obtaining is statistically significant because you're in 1D. So all the work is done in 1D. So very fast. Yesterday, Rachel Ward talked about, you know, the difficulty sometimes of storing all your vectors inside the matrix and manipulating that matrix. In this case, you can just stream the vectors one after the other and project them. And I see all the questions popping up. I think I'll ignore the questions just to get the point across first, and I'll look at the questions. So you let the vectors stream one after the other. You don't need to store them all at once, and you project. So it's, you know, very memory friendly. In addition to that, because the clustering is happening in 1D, you can work with a very small number of points. So if you have an application where you're trying to cluster, just say 20 points in, you know, a space of high dimension, and that's hopeless in the original high dimensional space. But once you're in one dimension, actually, it's quite possible that you can cluster them accurately in a statistically significant manner. So for applications like medical applications where you have very small number of patients that you're looking, this is a method that's actually quite friendly to that kind of applications. And of course, if you're concerned that linear separations don't exist in your data, and although it's, I mean, many cases it does. I mean, we've seen that high dimensional data sets can usually be clustered with these linear projections. You can also find nonlinear separation between your clusters just by using some kind of a kernel trick, just extend your feature space using nonlinear functions of your coordinates, and then do the projection. So then you get a nonlinear separation. So it's not restricted necessarily to just separating the data with a hyperplane, but you could have a nonlinear structure as well. So just, you know, very, very simple clustering method that, you know, yeah, does it work? Well, let's look at some data and let's see what happens. You know, does it work? We have a lot of experiments. I just selected a few to, you know, to display today to show that this actually works. That the data that we have in real data sets tend to really be amenable to this kind of manipulation and have a structure that's compatible with this kind of clustering algorithm. So let's look at 3 data sets. The first one I'm going to look at is the MFEAT data set. This is our feature representing handwritten numerals. There's 2,000 of them. And depending on the feature set chosen, we have different dimensionality. It can be very low. In the one case, it's only 6 dimensions. That's when the handwritten numerals are represented with morphological features. So, you know, back in the day, we developed some nice features for shape. It could be next higher up is 47 dimensions where we represent the handwritten numerals using Zernike moments. There's also some 2 by 2 pixel averages that gives us a 240 dimensional representation and so forth. So there's 6 different data sets representing the same handwritten numerals. We also have the dataset Libra, which has 360 points in 19 dimensions. These represent hand movements and sign language. And then there's the Mushroom dataset, which actually contains categorical data encoded using a one-hot encoding. So that has dimension 119 at the end of the day. So what do I want to show? Well, the first question you have is, you know, does this work? Does this sample clustering method actually find clusters in real data? So in these 3 data sets, we've applied this method to find clusters. And this graph represents on this axis the fraction of the NTARP runs that turned out to be to give us a statistically significant clustering. So to be clear, we take the data set, we project it on the random line, and we did that n times. And in this case, n was 50. So n is equal to 50. And then we take the best clustering paths that we found among those 50. And then we get a little bit of new data we haven't touched, and we check whether the structure we found is in the new data as well with a 5% confidence interval. That's what this is. And we wanted to see what percentage of the clusterings we found after these 50 trials ended up passing the test and being a statistically significant clustering. And it turns out that, of course, if you have a very small sample size, you know, you may not pass the test. But if you take, for example, 600 data samples in any of these data sets, the vast majority, almost all of the clusterings you found this way turned out to be statistically significant. So we do find things that are there in the data set. And we find them just at random, and a lot of them. Obviously this is extremely surprising. And for some of us to come from a probability background, you know, the first thing we think of is the Iaconis-Friedman paper from 1984 that said, you know, essentially under some very mild assumptions, most low dimensional projections of a data set, any data set, are going to be approximately Gaussian. You expect the projection to look like one clump that is Gaussian. So, you know, there's this whole community that work on this thing called projection pursuit, where, you know, they assume, you know, most of the projections are going to be not contain any information. They're just going to be one clump. So let's search for the very few that give us something that's not Gaussian, and we'll use that to characterize the geometry of the data set, right? But these are assumed to be very rare. And our experiment, that's not the case. You know, we get non-Gaussian projections fairly often, sometimes, you know, 60% of the time, 50% of the time, 40% of the time, something a little bit less, 10 or 20% of the time, but still a significant portion of these random projections are actually bimodal, which is very surprising. The other thing that is surprising is that because we draw our random projection vectors at random, well, if you pick a random vector, if you pick random vectors in a high dimensional space, those vectors are going to be nearly perpendicular, right? So we're saying that we're finding different clusterings with respect to vectors that are nearly perpendicular. So, you know, one clustering, let's see, I can't even draw a picture because how do we, you know, we're saying, okay, there's my data set somewhere here. I project it this way and I get a clustering structure that way. So that means there's a hyperplane separating the data very well this way. And then there's this other projection direction that's nearly perpendicular that also has a separation, right? So this implies that probably the grouping that we get with each clustering are not consistent with one another, right? Let's see if I have. Right, so you know, the groupings we're finding are statistically significant. They find structures that are there, and they will continue to be there even if I keep drawing more and more points and sampling more and more points from my initial density function. But the groupings they define in the original space are not consistent. So 2 points might end up together with respect to one clustering, and they may end up not being together with respect to another clustering. And that might seem a little bit wrong, right, when we think about it. But if we step back and think again about the problem of clustering, there's actually nothing wrong with that. And I like the fruit bowl here as an illustration. So if I ask you to cluster fruits, well, that's not a very well-defined question. So you might say, okay, I'm going to go and cluster them by colors. I think all the yellow ones, that's one group, and all the blue ones, that's another group, and so on. And I think everybody would agree that's a very fine clustering. But somebody else might say, oh, I'm going to group them according to shape. And I'll take the long ones and there'll be one group, and I'll take the round ones, it'll be another group. And that is also a correct way to cluster the data, but it's using a different criterion. So what we're saying there is that there's more than one criterion that you can use to cluster the data, and different criterions yield different groupings, yet each criterion might actually yield a statistically significant grouping. If that makes sense. And the other thing, of course, that we're learning from that is that empirical data probably does not satisfy the assumption of the Diaconis-Friedman theorem. So we'll dig into that to understand how, what is the structure of real data. Of course, somebody might say, well, are you sure? Are you certain that your clusters are there? Because, for example, there's this paper in 2018 that was published in the Proceeding of National Academy of Science by Bekelcourt and Nadler, in which they show that in many circumstances, if you have a finite set drawn from a Gaussian distribution high dimension, you can actually find projections that are going to be highly non-Gaussian. And in some cases, you can actually match any distribution you would like just by picking the right projection. And so, there's sort of a warning in that paper that we have to be careful that what we observe from a given set of points may not be there in the original data in the distribution that we're drawing from. So we have to be a little bit careful. We do have a statistical test in the way we run our distributions, but one might still say, well, we have a small number. Is it really there? Is it? We ran a lot of experiments where we started with a small number of points from a database, and we found some clustering structures in that small number of points. And then we expanded to the whole entire data set and checked, is it still there? And it turns out that, yes, the clusters we find with a small number of points tend to be there at the end. And the more points we have at the beginning, the more likely they are to stay there. So for example, if you have about 100 points, and these are the experiments with the previous data sets that I described, the NFEAT data sets with different features, morphological feature in the mushrooms. At 100 sample points, you see that 90% or more of the data, and it's really the pixel values of the end digits that's the worst. All the other ones are above 90%. Those structures we found on these 100 points turned out to still exist in the whole entire database. Once you're at 200 points to begin with, pretty much all the structure you find on the small number of points exists in the whole entire data set. So this is really a method that allows you to find structure, and really you don't need that many points. You will find structures in the one-dimensional space that are there in the higher, in the probability density functions that you're drawing from. So these are not ghosts, these exist in the data, and they're very, very interesting. All right, so this, observing all of this, of course, I was trained as a mathematician, so my question is always, what is it? What kind of structure in the data creates this phenomenon? We're observing data that does not necessarily have, probably does not have any clusters to begin with, and then we project it, and it has a high likelihood of clustering. So can we build a model? Can we build a mathematical property that will guarantee that this phenomenon will occur? So that's a question I thought about for a long time, and I asked a lot of people. And we have found a model that would explain what real data might look like. So if you were in the audience, this is always a fun time in the talk where we can actually start discussing, and people have different ideas of what it could be. If anyone wants to pitch in, what could it be? What structure in the data creates this phenomenon? No comments? All right, so it's definitely not a Gaussian mixture. Oftentimes we think of data as consisting of clumps. One clump here, one clump there, one clump there, one clump there, a bunch of clumps. A Gaussian mixture is a nice way to model clumps, and it's definitely not that. Data in high dimension cannot be clumps, because if you just have clumps and no other organization on top of it, you will not have that property. When you project, it's not going to create a binary clustering. So clumps are out. But anything else? All right, so let's build a model. So we know we're going to have to violate the assumptions of the Diaconis-Friedman theorem, because if we didn't, then the property would not hold. So what are those conditions? The first condition is that most points need to have nearly the same length. And the second condition is most points need to be nearly orthogonal. What we will end up violating is really the first one. So to build a model, we're going to start by putting the points on the vertices of a cube in RD. So you can put a point here, a point here, a point here, here. So this is dimension 3. So we have 2 to the 3. We have 8 points possible. In general, in the space of dimension D, we would have 2 to the D spots possible. So you can actually fit quite a bit of points there. So let's just put the points on the vertices of a cube in RD. And obviously, since it's a cube, those points do not form any cluster. There's no obvious way to divide the points into 2 halves where each group would be closer to its neighbor than they would be to the points of the other group. So we've got that first property. The other thing that's interesting about the cube is that different projections of the cube are going to yield different clusterings. So for example, if you pick this axis, and the axis that's aligned with this edge here, and you project all the data onto this axis, right? Then you're going to get that half the points will go here and half the points will go there. You're going to get a perfect clustering into 2 points. So that's a very nice clustering. And that clustering takes, this side of the cube and puts it in one group, and that side of the cube and puts it in another group. But you could also pick, say, this axis and project all the data onto this axis, in which case half the points, the ones that are towards us, would end up going to this point, and the ones that are towards the back would be mapped to that point. So you'd have a clear clustering this way. And this time the grouping would be different. You would have the top and the back in 2 different groups. So there's different ways to cluster the data depending on how you project it. And each clustering yields a different grouping. So we're on a good track. We've got no clusters, different types of clustering can be obtained, and depending on how we cluster, we have different groupings. So that seems to be compatible with what we observed so far. What we are missing, though, is the high probability of finding a clusters, because if you just have a cube and you pick a direction at random, if the dimension D is large, it's actually fairly unlikely that you're going to hit those axes. They're quite rare, and you have to hit them quite close to be able to separate the data, and the overall probability of separating ends up going to 0 as D goes to infinity. So it's not, it's a case of data where we would have to search a lot before we would find a clustering just by projecting at random. So we need to add something else that's going to increase that probability of hitting a clustering, and that something else is going to be a stretch. Now, I like, before I introduce the stretch, I like to view this data as a random process, because I think it's a little bit more enlightening. So the points of the vertices of a cube can be seen as, where does it say? And this would be the Bernoulli processes. So a Bernoulli random variable taking either value 0 with probability 1/2 and 1 with probability 1/2. So the first coordinate of the point is going to be either 0 or 1 with equal probability. And independently, the second coordinate is going to be 0 or 1 with equal probability, and so on until the D coordinate. So every one of the coordinates are going to be a Bernoulli process. And so you view your points as being an observation of these D Bernoulli processes. And when you say, oh, I'm going to project according to the first axis, let's say this one, then what you're saying is that this Bernoulli process represents your signal. Right? So you're projecting onto this dimension and you're killing all the other ones. So you're saying that the remaining Bernoulli processes are just noise, and you're going to ignore them because you don't think they give you information about the classification. So by projecting, you're making a choice. Where's your signal and where's your noise? And of course, if you make a different choice of what's your signal, what's your noise, you're going to get a different clustering. And really from the data standpoint, there's no reason why one Bernoulli process is more important than another one, is more information than the other one. I mean, in terms of data, it's the same thing. So it's really up to the algorithm to pick a process that will yield to a clustering. So So we're going to change that Bernoulli process. We're going to stretch out the different signals and make some signals have more strength than others. And that's how we're going to end up with these high probabilities. So essentially, we're stretching the edges of the cube. So for simplicity, I'm going to assume that A1 is the shortest, A2 is the next shortest, A3 is the next shortest. I'm going to order them in increasing order of magnitude. And what I'm doing by stretching these edges is I'm stretching the value of the Bernoulli variable. So the first one, Y1, is either 0 or A1. The second one, Y2, is either becomes 0 or A2, something slightly bigger, and so on. I have d random variables, and they're in their strength, their magnitude is increasing. Of course, we can set without loss of generality A1 equal to 1. That doesn't make any impact on the overall method. And so, yeah, so we're going to stretch the cube, and we need to stretch it in a clever way. We need to stretch in such a way that there's still no cluster inside our data, right? So we would like to have no cluster in the high dimensional data, but we would like to project to clusters with a high probability. So how do we do this? Well, if let's focus on the easiest way to cluster the data, the most obvious cluster in the high dimensional data, namely one where you take where you cluster with respect to the largest size, right? So you're saying everything on this side is one cluster, everything is on that side would be one cluster. So if you make A, D too large, it's going to separate the data into two clusters. The diameter of this here is, of course, the sum of the AKs from 1 to D minus 1, right? And same thing here. And this distance here is AK. So if you don't want to have clusters in your original data, you need your AK to be less than that. Okay. So we're going to use this condition here. In the worst case scenario, like the point where you start having, you're just about to get a cluster is when you have equality, right? So we're going to solve the equality case. So if the diameter of each cluster is equal to the distance in between, this would correspond to the case where AK is equal to 2 to the K minus 2. That's what we get from solving that recurrence here. So this is sort of the worst case scenario. And in general, we could say AK squared is R to the K minus 2, and R will go between 1 and 2, where 2 will be our worst case. So let me summarize a little bit. When R is equal to 1, the scaling factor is equal to 1 for each edge, and so we have a cube. And as I increase R, then the dimensions start changing like this. And of course, the AD is the largest, and AD minus 1 is a little bit smaller, and so on, but they have this exponential relationship between them. So if I do it this way, if I say that my scaling factor is AK equal to some constant R between 1 and 2 to the power K minus 2, then it turns out that projecting my cube has a very high probability of yielding a very nice clustering. This is an empirical graph of the probability of a good separation for different values of R between 1 and 2. And you can see, for example, that at 1.4, you stretch your cube just a little bit, not completely out. You have over a 40% probability to find a clustering when you project at random. In the different dimensions that we tried. So the dimension 3, of course, is up here. Okay? So this has a very, very high probability of splitting into 2 by random projection, about 90%. As you increase the dimension, the probability decreases all the way down. This is dimension 100 in purple. But even in dimension 100, which is a fairly high dimension, you have about 30, I don't know, close to 40% probability of finding a clustering when you project at random. And so this model seems to fit the bill. It has all the right elements. And you know, it really teaches us something when we try to imagine what data looks like in high dimension, is that, you know, your data points is a result of different phenomena, you know, noise, and, you know, there's different things that influence what your data, the values of your data point. So when you project, you're picking which of these phenomena you're going to declare noise and which of these phenomena you're going to declare to be signal. And there's different choices you can make, and different projection, different choices are going to lead to different clustering, and that makes sense. So really the clustering paradigm really needs to be rethought a little bit, and that it's not that there's just one clustering of a data set, but there, you know, there may be several. And each of these clustering actually tell you about the structure of your initial data set. So, you know, what is the model? Well, the model, I mean, I'm not saying that all data looks like a cube, but it's approximately like a cube. It's far away points, but in different dimension, they're far away at different sizes. And because we project everything to, you know, some manifolds or structures, or we end up collapsing some of these dimensions and then creating clusters. But different structure will lead to, you know, different structure chosen for projection will yield to different structures in the clustering that you obtain. And that's really a consequence of your choice of algorithm, or you know, your seed, or your, it's in a way, I don't want to say an artifact because the structure is there, but it results from your choice of method for projecting. And so I think that's a better way to picture high dimensional data. Right, and so you definitely don't want to think about high dimensional data as clumps, right? Something like this. That's just not, this is really not an accurate picture for high dimensions. It's really, you know, things are far away, very, very far away from one another, and the structures you find really exist only once you start getting rid of some of those dimensions, getting rid of some of that space. So that's for the model. Obviously, the stretch was very, very important in the cube to get that high probability. So I know a lot of people will tend to whiten the data before they find clusters. And what whitening would do to the cube is to the stretch cube is it would send it back to a cube of regular size, right? So that would not be helpful, because all of a sudden it would be very, very hard to find these separations. And we're well aware of that when you talk about clustering, really. Stretching the different dimensions can essentially destroy your clustering structures. So you have to be very careful when you do that. So this brings up, it's 42. I'm just going to bring up a couple ideas. Now that we know that we can find some structures by random projection, then you can ask, well, if I can measure this probability of getting a random of a structure by random projection, could I somehow compare data sets? Right? And if I could compare data sets and find the ones that are very likely to cluster by random projections and whether or not, then, you know, I might have an idea of which data, you know, compare different data sets. I mean, obviously, if you want to test an algorithm and your data is super easy to cluster, maybe that's not the best data sets to play with, right? So, so there's different ways where you can start playing on this idea and measure clusterability. So we have different methods. One of them is you do a bunch of projection of your data sets, and then you measure to what extent these projections are separated into two. And if you have a measure of that separation, let's call it S, that measure is a random number. So you can draw the probability density function of that measure. And that probability density function is really going to measure something about the structure of that data set, so then you can compare data sets. So this is the probability density function of a measure S that measures the separability of the projection. And the lower it is, the more separated it is. And so you can take, I do have some data sets here. You can take like the Amphi data set and draw this probability density function, and this is what you get, like this little bump here. And you can compare it with another data set. For example, on top of it in dotted, I have a Gaussian, what a Gaussian would give you. And so you can see it's a lot more organized than a Gaussian. In fact, all these the values here correspond to projections that are very, very separated. And this is one of those very separated projection that you see here. And it's extremely separated and was found at random by a random projection. Yet if you draw the, if you try to understand the structure of the data set by plotting the probability density function of the pairwise distances between the points, like so here, you get one clump. So there's no information there. So this graph here is a very nice way to compare data sets. And I'm going to move to my conclusion slide here. So the fact that you can find these separation structure by projection, it allows you to compare data sets. It allows you to compare how data sets change when you use different features. I have some examples I can show if people have questions later on, where you change the feature set and you see how much structure you create that way. Sometimes you make it better, sometimes you make it worse. For example, can we use that to understand how the different layers of a neural network is transforming the data? How, are we adding structure? How are we changing the structure? Can we use that to build adversarial attacks? Because if a data set has separations, well, close to the separation usually is where you have empty space. That's where you have not really where you don't do a very good performance necessarily. And so what if you generate examples in there to fool a classifier, for example? Can we use that to build test databases that are going to have fewer holes and make sure that you're going to cover more space and things like this? So I'm going to just put this there. I think my time is up and I'm happy to answer questions.
Great talk. Thanks very much to finish on time. I saw there are several questions in the box. Before that, let me ask you a question. So you said actually when you everything here is based on probability density distribution, right? PDF. But most of case you only have data, you don't have PDF. So how can you deal with that?
Right. So if you have data, then you have to view them as samples, and you have to be careful that you do all your learning with one set of data, and then you keep hopefully an independent set of data that you have not touched ever, and then you do a thing on it to make sure that
But you want to learn the PDF first.
So in this case we're not learning PDF. We're just learning separations. We're finding good separations, and so you find the separations from some data, and then you check, is this still a separation in the new data, essentially.
Oh, I see. Okay. Taras?
Someone asked a question, what about outliers?
Yeah, I mean, you can have outliers in the, I'm not sure what the question was referring to, but yeah, when you cluster, obviously there's, it's usually not a perfect clustering, right? So there's a little bump and a little bump. It's really like in the picture, maybe I'll show the picture how we clustered it. So there's a separation of the data into two, where did I want? Yeah, there's a separation of the data into two lines, into two sets. The PDF, here you have a histogram that represents it. So on the right-hand side, you have one group, and on the left-hand side, you have another group. It's like a class when you do by using classifier. You class 1 that has this probability density function. Class 2 has this probability density function. You do have a classifier. It's not a perfect classifier, right? There's always going to be a little bit of overlap between the densities, but the best possible separation between the two can be obtained, can be estimated from an estimate of the probability density function of each. So there's no problem with having outliers in this setup. It's really fundamentally a statistical way of thinking about the clustering problem.
So sort of continuing along that line, you could do more than binary here, and then is there a possibility you'd end up with some really small classes that only had a few elements?
Yeah, so we actually did it in a hierarchical way the first time we started playing with that. I have some results where we built a hierarchical clustering method, and we actually benchmarked it against other existing clustering methods. And ours is, of course, super fast because it's cluster binary divided into cluster binary divided into, and just have some kind of a stopping criteria. And it actually performed better than the existing algorithms in many different measures. And so we're very surprised at how accurate it is. And so it's not just a binary clustering method. You can combine it into different ways to get several classes down at the end. And it's very, very accurate. And the reason why it's accurate is every time you separate, it's in 1D. So you can always check the statistical validity, do a statistical test. Like, do I really have a separation there or not? And so to make sure that what you're finding is statistically significant.
Someone asking about how entropy can be useful in describing the high dimensional data sets.
So the thing that I'm trying to avoid is to play with the high dimensional data set directly. So what I would love to have, essentially you have something about the entropy of the projections telling you about the entropy of the original set, right? So normally you would expect that when you project your data set, the entropy becomes trivial. There's really no information to be had. But yes, now that we see that there's some structure in those projections, we might be able to, at least theoretically, come up with some relationship. This is what it tells me about the entropy of my original data set. So computing the entropy in the original data set in high dimension is really, really difficult, right? But if we can infer the high dimensional data set structure, its entropy from the projection, I think that'd be very nice.
But do you think in terms of like the model, assumptions, if we made assumptions about entropy on the high dimensional data set, would that tell us about the type of clusterings we would expect?
I don't know. I mean, I've looked for different models, and that's the only thing that made any sense for us. And I've looked at sparsity assumptions. I was also thinking what would create what we're observing. The only thing that really worked was that, but I'd be happy to see if there's another interpretation of what would create this phenomenon. And if it's in terms of entropy, that would be very nice.
Someone also asked what the clustering was supposed to represent, I think, in the mushrooms. She says, what are you looking for in the mushrooms?
Well, so you're just looking for groups. So the mushrooms, they have different characteristics. I'm not a mushroom expert, but this was written by like expert mushroom pickers. I don't know, like colors and shape and like really discrete features that are then written as 0, 1, 0, 0, 1, 0, 1, depending on which feature are present in that mushroom. And then we're just looking for classes of mushrooms that would naturally occur. And so, of course, if you say, well, I'm going to look at shape of the mushroom, then I'll get one clustering, and it's a very easily clusterable data set. But likewise, the morphological feature, the 6 features for the mathematical morphology features representing the handwritten digits are super clusterable as well. So there's some features that are really, really easy to cluster.
Let's see, that's all in the Q&A. So if anyone from the panel has questions and wants to...
Jinzhao, you can ask your question.
If there are no other questions.
Yeah, it's
Well, this is a very interesting talk. Thank you. And let me try to understand what I learned from here. So you project this high dimensional data into a randomly chosen one-dimensional direction. So there's a good probability to identify the cluster, right?
Yeah, to find a structure. And I know I'm stirring the pot here because nobody expected that. We all want to have complicated algorithms so we can. This is too simple to work. The problem is it works.
Well, this is quite remarkable. Another thing is that I like your statement, you call it no cluster in high dimensional data. That's quite an affirmative statement. Do you have a formal mathematical description of that statement? Or?
Yeah. So, essentially it's, any metric you put in your space, you will have, you don't have accumulation points when you draw a sequence of points in a high dimensional Hilbert space. The sequence can, you can have an infinite sequence inside a cube, for example, and that sequence will have no subsequence that converges. So you have no accumulation points.
So another way I'm going to try to understand, I really love your example in the very beginning. If you shrink the unit ball in a high dimension with epsilon size, the smaller cube is goes the metric goes to the volume goes to 0. And so that's probably, so if you give a lot of data, it's going to be highly concentrated on the boundary. So there's not much room around the boundary, so you cannot separate them. Okay, so that's probably, but now here's the most critical point in this argument is that you use the Euclidean metric. Euclidean distance. And but if you use this language, maybe we can say that to make the high dimensional data clusterable, we will do the classification. You just have to somehow cluster and make them, into
so any metric.
Basically, you want to find a good metric.
Yes, it's going to have to be degenerate though, because any metric you put on your space is going to have the same property that any cube defined with that matrix will have a zero volume inside.
You think it has to be degenerate? Let's, for example, take the support vector machine. You have kernel method. So my understanding of a kernel method, you take whatever, you know, a linear separable or whatever linear algorithm model, you replace the inner product of the data by this kernel. That intrinsically introduce the metric, which pretty much is like a different metric. Another way to say that there's an implicitly defined feature map from this kernel. So you in the featured space, which you argue should be low dimension. But I think in this support vector machine theory, I still couldn't read those big books. So you can argue that, wow, my feature space is actually very high dimension. Single dimensional. Then you take the Hilbert the metric, maybe the whatever, maybe Euclidean dimension distance. So I guess the challenge is that in the machine learning is to actually to learn what kind of metric you're going to use. So maybe it is probably
very important. So when you use a super vector machine, you embed your feature into a higher dimensional space. You only embed on a subspace. Right, yeah, because everything is the same dimension as you started with. You know, if you have 4 dimensions, you still have 4 dimensions, but embed in higher dimensional space. When you pick samples, they have to lie on this 4-dimensional subspace. The PDF is generated.
Very good. Yeah, now I got you. Is that all this feature, all these things should be low dimensional, what some people may call it feature extraction. But the remarkable things you have told us here is that to a simple projection, randomly chosen direction, you can also identify this feature somehow in a very high probability way. Am I correct? This is very nice, very interesting. Thank you very much.
Thank you.
Any other questions?
So there's something about the proof that 1 minus epsilon, and this is very well known. It's in, you know, it's usually in machine learning courses. We go through that once and for all just to clarify things. But I very much agree with this. One needs to be very, very careful with high dimensional objects because our intuition does not hold to high dimension.
Okay, good. Thanks, Marie, for a wonderful talk. So then let me conclude our today's morning session, and thanks again for our 3 speakers for giving wonderful talks. And also thank you guys for coming and participating. So let's have a short break, and our afternoon session will start at 2 p.m. Eastern time, about in 1 hour. Okay, see you guys.
Thank you.